Hello, welcome back. Today we will speak about a different kind of things. So far we have spoken about analog circuits. Today we start speaking about digital circuits. We need to understand a couple of fundamental things. So by digital circuits, I mean circuits that can have two states, the so-called 1 and 0. So in electronics, those values are represented by levels of voltage. Usually the zero number, let's say, zero value is represented by a low voltage. So let's say 0 for us means low voltage, and 1 conversely means high voltage. So there is a standard for these voltages. So the old standard is that low is 0 and high is 5 volts. And a more modern standard is that the 0 level is 0 volts and the 1 level or high level is 3.3 volts. Okay, so most of the time you will find those two standards. So what does this mean? It means that we have circuits, we do something on them, we activate, they produce outputs, but the only two possible values are low or high. So let's say 0 or 1. So with this idea we can represent numbers. So here we have an example of how we can represent a number in the so-called binary code. So it's very similar to what we do for decimal numbers, because if I say, for instance, the number, okay, here we have 25. So 25 is 2 hundredths plus 5 units. So in decimal, the unit is the number 1, which can be represented as 10 to the 0, and the 100, sorry, 100, it's not 200, it's 2 decades. And so decades is 10 or 10 to the 1. So these numbers are called base 10 numbers, because the base of this exponent is 10. Now we have binary numbers, so we have a base 2 system. The base is 2. So with the same idea of decomposition, we can write such kind of number as, let's say, 1 unit, but it's not called unit. So 2 to the 0, which is 1, plus 0 multiplied 2 to the 1, plus 0 multiplied 2 to the 2, plus 1 to the, and so on. And then if we perform all this multiplication and we add everything together, then we have those numbers and we compute the sum, and this is the number converted into decimal form. So the opposite is also possible. From having a number into decimal form, how can we convert it into binary form? So the algorithm is quite simple. We do a series of divisions by 2, and we keep the remainder of the division. So for instance, here we start from the number 25, of course can be any number. 25 divided by 2 is 12, and the remainder is 1. Then 12 divided by 2 is 6, and the remainder is 0. 6 divided by 2 is 3, and the remainder is 0. 3 divided by 2 is 1, and the remainder is 1. 1 divided by 2 is 0, and the remainder is 1. And then we read all those reminders backwards Okay, this is the procedure. It can be demonstrated. It's like this. So if you read all of them backwards, you have 1 1 0 0 1, which is 1 1 0 0 1. So with simple rules, we can convert a binary number into a decimal and a decimal into a binary. So why we need to use binary numbers in electronics? It has not been like this all the time. So those numbers are useful in order to do computation. But in the beginning, people started thinking, of course, of doing computation with decimal numbers. So the very old computers, computers originally developed by the fathers of the computers, like von Neumann or Alan Turing. In the beginning, those first computers were using decimal numbers and were using decimal level of voltages in order to represent the different numbers. But they quickly understood they had problems related to noise. So if you want to represent very big numbers, then at a certain point you need to have an enormous amount of levels of voltages, and you can imagine that if your range of voltage is limited because of the power supply of the amplifiers involved in these things, then let's say the delta V between one difference of voltage between one level and another one becomes so small that a little bit of noise present in the environment will easily corrupt the digits. So they start thinking how to simplify this, and in the end somebody, I don't know who, had the idea that only two levels of voltage are sufficient in order to do this. So let's go to the binary numbers. We can make two levels of voltages quite distant each other. The distance can be much bigger than the noise level that might be present in the system, so we are able to identify with some thresholds which is the zeros and which are the ones. And this is why we have this nowadays basically in every computer. Okay, so then there are another couple of things we need to speak about. So there are theorems, laws, such kind of things, mathematics. So one very important set of laws are those two laws, which are called the De Morgan's laws. So here we have a picture with a representation of sets, which can be read this way. So here x and y are two variables. Those two variables are binary variables. They can have either 0 or 1 as a value. So one operation that we consider is the so-called not operation, or also negation, but let's say not, as usual. So here what we have is an environment, a set, and then a subset, or let's say better, the round circle, the circle is a set and the other one is the environment in which this set is placed. So we can say that those are elements of x if they are inside these boundaries, and the ones that are not elements of these sets are the ones outside, so the ones that are falling into this region. So similarly, there is another operation which is called OR, that it's an operation that takes two operands, x and y. So a number, the result of this OR operation, is the one that belongs to one set or another one, or both. So it's an inclusive or. So we are speaking about all those numbers, elements that are present here. When we speak about doing the AND between two sets, we are basically thinking of the intersection. So for us, elements that are belonging to the AND of two sets are the ones that are simultaneously present in one set, so in the X set, and the Y, and they are only those ones. So what the De Morgan's laws are saying, let's start for instance with the first one. It's a sort of equivalence. So let's do this. Okay. For instance, let's look at this one. It is saying that the knot of X, so let's try to find a set which is X and calculate the knot of X. For instance, here we have X. The knot of X is the set of the elements that are outside X. So all those elements here this is the knot of X. Similarly, the knot of Y are all the elements that are outside the Y set, so which is all now we have to do it carefully, all those elements okay. So this thing is saying that if I take either the elements from here or here, so the blue and the yellow, this corresponds to the knot of X and Y. So the X and Y was this set, the intersection, and so therefore the knot of this intersection is the part which is outside, which is the blue merged with the yellow, which is what is written here. So by this we verified the first law, and similarly we don't do this, we can apply the same reasoning in order to verify this one. So another thing that we might say is that there are those symbols, but most of the time the not operation is indicated like this, with a bar over the variable. This means not. Then the OR operation most of the time is indicated with a plus. This means OR, and the AND operation is indicated with a multiplication. We will see why in a moment. Okay. So now we can speak about those operations, and we can introduce two concepts. So one concept is the concept of truth table, . And the other concept is a set of symbols like this one corresponding to the representation of an electronic device that implements the truth table, and those devices are called logic gates. So the truth table is something like this. It's a table that identifies all possibilities of all possible states of a logic gate. So here we have these symbols. They are like again black boxes. So there is something inside, and there is an input and an output. Or I can have situations like this one where I have multiple inputs, let's say X and Y, and one output. We will see that there are circuits also with more than one outputs. So I can have many inputs and many outputs. So now I want to be able to define a circuit that works like this. So it has an input we call X, and the output let's call it A, behaves like this. So the output is A. If the input is 0, we want to have the output to be 1. If the output is 1, we want to have, if the input is 1, we want to have the output to be 0. So this corresponds to the NOT operation. So let's say like this, A would be equal to X naught. So such kind of circuit, if it exists, it will calculate these things. Very elementary calculation. And similarly, we might want to have another behavior like this one, which is called the AND behavior. So we have now a circuit with two inputs, X and Y, and an output A, where A is the AND of the two inputs. So we want to have something that according to all possibilities of X and Y, and I want to stress the point that there are only a finite number of possibilities, because we have two variables, two states, and so we have only 4 possibilities, 4 combinations for the inputs. There are no other states that are possible for the input. So we have to analyze all those 4 states and ask what we want as a behavior. So we said that we want a circuit that calculates the AND. The AND operation is the one for which we take the intersection of the two sets. So we want to have an element in the AND set only if that element is present simultaneously on the X set and Y set. So only this condition will produce a 1 at the output. All the other conditions will make a 0. And now we can start to see why we have this multiplication sign, because if we consider this into a binary system, so 0 multiplied 0 makes 0, 0 multiplied 1 makes 0, 1 multiplied 0 makes 0, and 1 multiplied by 1 makes 1. So the AND operation is a sort of multiplication between binary numbers. And similarly, we can do for the OR operation. So this thing is called OR gate. And I apologize from the very beginning, but in this part of the course there will always be a lot of ambiguity when I will say let's take an AND gate and a NOR gate. So we have to be careful. They are called like this. I'm sorry. So the OR gate, if we think at the sets corresponding to the operation, has this behavior. So we want to have the result of our operation A to be part of the set of the output when Y is present in the set, or X, or both. So we have this behavior here, and the only case that makes it to have our output to be 0 is this. So in this case this is indicated with the plus, and again it's not an exact summation, but if you consider that 0 plus 0 makes 0, and 0 plus 1 makes 1, and 1 plus 0 makes 1, 1 plus 1 doesn't make 1, but say it's a sort of summation. So as a reminder of this thing, usually this operation is indicated like this. Okay, so we have to understand what are those things. How can we design circuits that will produce this? The simplest one is the NOT gate, so let's start with this one. Okay, this is an implementation of the so-called NOT gate. We already met this circuit here. It's the output stage of an operational amplifier. So you have to look now at this a little bit more carefully. So we said that this thing is a sort of voltage divider. So two resistors like this. Let's say R1 and R2. But the resistance of those two resistors are controlled by the gate voltage. So now we have two transistors, one which is a N-type and one which is the complementary type. So this is the so-called CMOS technology. Our variable, the input, now is called A, is connected to both the gates of the transistors, but they work in a complementary way. So if the signal A is high, so let's assume that this thing is high respect to the ground, so it means that A is equal to 5 volts at this moment, then the low transistor will conduct, meaning that the R2 will be very small, let's say almost 0, just to be clear. So if this resistor is almost 0, let's see what's the value of this one. So when this is high, it means that this thing is connected to 5 volts, so the gate of this transistor is connected to the same value of the drain of this transistor. So if this transistor was an N-type transistor as the one we studied, it means that when the gate voltage is equal to the drain voltage, we have exactly the opposite situation. So the resistance is very high here because the channel is not formed, is completely closed. Remember that the width of the channel, the thickness, was created by a voltage in the gate attracting electrons from the bulk. So if this voltage, gate voltage, is not present, and it's not present, it means that it is equal to the drain. So it's like as this battery has a 0 voltage, so the resistance is high. Similarly, it works for the complementary part here. So when this is high, the gate of this is equal to the drain of this, and this resistor is kind of infinitive, which for us means that is as like as it's not connected. So then we have the situation that this voltage divider under this condition is equivalent to a non-present resistor here and a resistor which is close to zero here, which means that this point is short circuited directly to ground, and so therefore its value of voltage is low. So high at the input makes low at the output, and vice versa. So we can repeat the same reasoning, and if we do this, we will have exactly the opposite. So if we put a low signal at the input, we will have then that this resistor is close to zero and this resistor is close to, let's say, infinity. So this one would be the open circuit, so it's like as it's not present, and this one would be a short circuit, but this time to VCC, so the output would be high. So high input, low output, low input, high output. This is exactly the NOT gate. So this circuit is implementing the NOT of our variable. And from, let's say, a note from the theoretical point of view of this kind of things, it is interesting to notice, not for us in this course, but let's say it's a result of all these theories about the designing of these digital circuits, that this circuit, from a formal point of view, is divided into two parts. The so-called pull-down network and a complementary so-called pull-up network. It is possible to demonstrate that all these type of circuits can be represented by such kind of two separate circuits. So the input splits to a pull-up network and to a pull-down network, and those networks are, we will see with some examples, complementary in a sense.